Welcome to UXL, where you can learn new skills anytime and anywhere. Visit uxl.com to explore our full course selection. This lesson is part of a larger course. Check the video description below for a link to the full course where you can enroll. If you enjoy our content, please like and subscribe. For your convenience, the course cover displayed on your screen provides the complete course title and lesson title. Let's proceed with the lesson. Lesson: Training machine learning models. Training machine learning models involves a series of critical steps that require a deep understanding of both theoretical concepts and practical methodologies. The process begins with data collection and preparation, which is paramount since the quality and quantity of data directly influence the model's performance. Data must be relevant, diverse, and accurately labeled to serve as a reliable foundation for training. This stage often entails data cleaning, dealing with missing values, and normalizing data to ensure consistency. Techniques such as data augmentation and synthetic data generation can be employed to enhance the dataset, especially when working with limited data. Once the data is prepared, the next step is selecting an appropriate model architecture. This selection depends on the problem at hand: classification, regression, clustering, or any other machine learning task. For instance, convolutional neural networks are particularly effective for image recognition tasks due to their ability to capture spatial hierarchies in images. On the other hand, recurrent neural networks and their variants, like long short-term memory networks, are suitable for sequential data such as time series analysis and natural language processing. The choice of model architecture is crucial as it determines the complexity and capability of the model to learn from data. After selecting the model, the process of training begins. This involves feeding the model with training data and adjusting the model parameters iteratively to minimize the error in its predictions. The training process uses algorithms such as gradient descent, which optimizes the model by minimizing a loss function, a measure of how well the model's predictions match the actual data. Techniques like backpropagation are employed to calculate gradients and update model weights efficiently. The learning rate, a hyperparameter that controls how much the model is adjusted with respect to the loss gradient, plays a critical role here. If the learning rate is too high, the model might converge too quickly to a suboptimal solution. If too low, the training process becomes excessively slow and might get stuck in local minima. Regularization techniques are essential to prevent overfitting, a common problem where a model performs exceedingly well on training data but poorly on unseen data. Strategies like dropout, which randomly disables a fraction of neurons during training, and L2 regularization, which penalizes large weights, help in maintaining the model's generalizability. Additionally, cross-validation, particularly k-fold cross-validation, is a robust method to ensure that the model's performance is consistent across different subsets of the data. Another critical aspect of training machine learning models is hyperparameter tuning. Hyperparameters, unlike model parameters, are set before the training process begins and include factors like the number of layers, number of neurons per layer, and learning rate. Techniques such as grid search, random search, and more sophisticated methods like Bayesian optimization are employed to find the optimal set of hyperparameters that yield the best performance. This process can be computationally intensive, but is crucial for maximizing model performance. The evaluation of the trained model is conducted using metrics that quantify its accuracy, precision, recall, F1 score, or mean squared error, depending on the task. For instance, in classification tasks, the confusion matrix provides a detailed breakdown of true positives, true negatives, false positives, and false negatives, which helps in understanding the model's performance beyond mere accuracy. It's also important to use a separate validation or test dataset that the model hasn't seen during training to assess its performance objectively. Cross-entropy loss is commonly used for classification tasks, while mean squared error is used for regression tasks. Once the model demonstrates satisfactory performance on the validation set, it can be deployed in a real-world environment. However, the training process doesn't end here. Continuous monitoring of the model's performance is necessary to ensure it remains effective over time. Models can degrade due to changes in the underlying data distribution, a phenomenon known as data drift. Techniques like online learning and periodic retraining with new data can mitigate this issue and ensure the model adapts to new patterns and trends. Training machine learning models also involves understanding the underlying ethical implications and ensuring fairness and transparency. Bias in training data can lead to biased models, which can propagate and amplify existing inequalities. Techniques for detecting and mitigating bias include fairness-aware machine learning algorithms and regular audits of model performance across different demographic groups. Transparency in model decisions, often achieved through explainability techniques like SHAP values or LIME, is crucial for gaining trust from users and stakeholders. In addition to technical considerations, resource management is a significant part of the training process. Training sophisticated models, especially deep learning models, requires substantial computational resources. Graphics processing units and tensor processing units are commonly used to accelerate the training process. Cloud computing platforms like AWS, Google Cloud, and Azure provide scalable solutions for handling large-scale computations. Effective resource management involves balancing the cost and time efficiency without compromising the quality of the training process. Finally, model interpretability and explainability are essential for practical deployment, especially in critical areas like healthcare, finance, and autonomous systems. Understanding how a model makes decisions can provide insights into its reliability and robustness. Techniques such as saliency maps for CNNs or attention mechanisms for RNNs can highlight which parts of the input data are most influential in the model's decisions. These insights not only help in debugging and improving models, but also in ensuring compliance with regulatory requirements and ethical standards. The process of training machine learning models is complex and multifaceted, requiring a blend of theoretical knowledge and practical skills. From data preparation to model deployment and continuous monitoring, each step is critical for developing robust, efficient, and fair models. By understanding and applying these principles, modern leaders can harness the power of generative AI and machine learning to drive innovation and solve complex problems. This concludes the lesson. We trust you found this video informative and engaging. To enroll in the complete course, please use the link provided in the description below. At UXL, we are committed to your learning journey. Each course offers a certificate of completion, online support, and downloadable resource files to enhance your experience. If you found our content valuable, we invite you to like this video and subscribe to our channel. Thank you for joining us, and we look forward to supporting your continued pursuit of knowledge.